My name's Ash Lyons. Join me as I try and figure out what quantum science is really all about. Welcome to Cracking Quantum. So the ticket's a really nice place to be. Are you in the building?
No, I'm across the road in the John Anderson, so it's which, as I said, we're getting refurbed. So this one, I guess it's kind of our version of the Ark, right?
Yeah,
it's the same kind of thing. Although it was around a couple of years before that, and I think it's worked quite well actually.
Yeah. You can definitely see that that's the model that Glasgow Uni has taken and kind of run with. It's like you say, it has a very similar feel. It seems like this is always going to be a problem with physics departments being in usually quite old buildings or from the 60s.
Yeah.
That you're in this constant state of needing refurbishments all the time.
Yeah.
It creates a lot of chaos.
Well, we've only just recently got the asbestos taken out of our building, right? That was last summer.
Yeah.
And so now they're doing the full refurb of the heating, the windows, and the cladding of the building. So it's been quite a year of upheaval, and to just come into a shiny new building like this is probably would make sense, but then of course you always get the office problems that you've mentioned.
Yeah.
They never want to give you your own office where you can meet students and confidentially and things like, which is sometimes what you need. Yeah.
It seems like it's a really important point that people within the building management and design really kind of miss, is you want students to be able to come up to you and ask you questions, not just for like the scientific discussion reasons, but because students need support sometimes, and they need a place where they can actually just come and have a conversation with just you, which doesn't really happen if you just got a communal office environment. It's not going to make sense.
It's kind of almost like the staff room at school. Students don't want to go into the staff room at school, do they?
Our building in Glasgow, I mean, we've completely locked off the students essentially because we've got barriers that stop the students from getting to the research floors. So they have to go to reception, get a card to sign in. And of course, they're not going to do that. It's just not going to happen.
No.
So coming on to the actual podcast, I've got Professor John Jeffers with me today from the University of Strathclyde. Hi, John.
Hello. Good to be talking to you, Ash.
Good to be talking to you too. There's something that I think that would really help at the start of this podcast series that I haven't really covered with anybody yet, and that's to look at a few of the definitions of the specific words that we use within quantum science and technology.
Sure.
To really give an overview, a perspective as to what some of these terms mean.
Okay, yeah.
So let's start with a nice, easy one, as we were just discussing a few minutes ago. What is quantum? How would you define that?
Yeah, so quantum at some level is just about it's the physics of the very small. When we look at things in our everyday life, we see things that are the same size as us, and they behave in a particular way that we all seem to understand. They're solid objects that we can move around, or liquids that move around. They obey Newton's laws, which we kind of remember from school. But when we look at smaller things, we see that these rules are not necessarily obeyed all the time. They're obeyed on average, but they're not obeyed exactly. And so we can kind of see deviations, changes to the rules. And that's, whenever we see these deviations, this unusual behavior, we think that's quantum.
Yeah, okay. That makes a lot of sense. There's always a problem I have with this kind of definition though, because I come from an optics background. Mm-hmm. So what does very small mean in this sense? I mean, it makes sense at looking at atoms and molecules, and if we look at individual small clusters of molecules or atoms, they start to behave differently. But if I ask the question instead, well, what does quantum light look like? Is that small in a similar kind of way?
So small in terms of light probably means not very bright. So we
Okay.
when we think of like sunlight's quite a bright form of light. Our eyes can see lots of light, and we can detect. We're basically seeing the effect of many. Well, here's where I'm going to introduce my first quantum word, right? Many individual photons. Photons are the kind of the fundamental individual parts of light that we can't divide. They're elementary excitations of the light field. They're the smallest amount of light you can get. And normally we see lots of these with our eyes, and so we can't see the effects of individual ones. Mm-hmm. So in some sense, small for optics means having only a small number of these individual excitations.
Yeah, I think that's a really good way of putting it, because if you start to think about in terms of, usually we measure light using things like intensity and energy, but all of these are continuous, essentially. Whereas when you get down to the really low levels of let's say, intensity, you get down to individual quantized photons, so where you take leaps in distinct amounts of energy that we...
You can catch them one at a time.
Yeah, that's a good way of putting it.
And that's not something we can easily do with kind of normal, intensity measurements that we would do.
Yeah.
So, but we try and do that in the lab, I guess. You're an expert in this kind of area.
Yeah,
try and catch individual photons in the lab, and we can do it nowadays.
So I guess we can come on to some of the answers to this question with, actually that's the later questions I'm going to ask anyway, but what is it about catching light one photon at a time that gives you different behavior? What's the different behavior that you see when it's just one photon at a time?
Well, so light is, classically we think of light as being a wave. Okay, so the wave nature of light, we can do interference experiments with. So what that means is if I take a single source of light, I split it up and make it go two ways, I can bring it back together, and at different places I can get very bright bits and dark bits. We call them fringes in optics. So whereas if I cut off one of those split beams, we don't see those fringes.
Yeah.
So somehow magically the two beams affect each other such that you get bright and dark fringes.
Yeah.
So light doesn't, they interfere. The two beams interfere. Now, so we know that light's a wave in that sense, and it's not supposedly therefore made up of particles, because particles, if I tried to do a similar thing with bullets, for example, if my try and split bullets into two, then I wouldn't get such an interference pattern. You can't split bullets.
Yeah.
You're not going to get that. So the first thing that we see, I guess, that says things are quantum, due to the fact that light actually comes in these lumps that can't be divided.
Yeah. And
we see statistics that show that basically light is made of photons, not just a wave.
Yeah. That leads in quite nicely, I think, to the next question I was going to ask, which is, we use this word superposition a lot. It's not a word that's exclusive to quantum mechanics when we're talking about it.
Yeah.
But it is a word that we use quite a lot. So what does that word actually mean within the context of, let's say, a single photon inside an interferometer like you're talking about before?
Okay, so I've kind of sort of been suggesting that these particles are indivisible, and they are. Single photons are indivisible in that way. But they can do things that we really can't, or I say they can do things, I'm giving them qualities that they don't actually really have, of course, but they appear to be able to do things that, for example, bullets wouldn't be able to do. indivisible elements wouldn't be able to do. If I split them at, say, an element called a beam splitter, so a beam splitter is a kind of like a 50% mirror, so it would reflect half of the light and transmit half of the light. So if I have individual photons, if you do that experiment with individual photons, you send an individual photon onto a beam splitter, it either gets transmitted or it gets reflected with 50% probability. So it kind of flips a coin, says I'm going to be transmitted through the beam splitter, or I'm going to be, or if it gets the other result, it gets reflected. And we can put detectors in the outputs and test that. Then if we take those outputs, instead of detecting them, and we recombine them in another beam splitter to form an interference experiment, then we can find that in fact things are not random at the outputs. You might think, right, so if the photon comes and hits the first beam splitter and is reflected, and then we take that output and make it go to a second beam splitter, and then at that beam splitter the photon is either reflected or transmitted, you might think, well, there's a 50% chance of it going one way or the other, because we know how beam splitters behave. They behave like a coin flip. But it turns out that if you do that interference experiment with both arms, the transmitted and reflected arm, let them both hit the second beam splitter, we can adjust those two arms such that all of the light always comes out one port.
Yeah.
So the single photon, although its path is random within the interferometer, when it hits the second beam splitter, it's no longer random.
Yeah.
It definitely goes one way, which seems very weird. Now we sort of say that when the photon is in the middle of the interferometer, it's in a superposition of being transmitted and reflected.
Yes.
So it's in a kind of superposition of two classical possibilities.
Yeah.
And we require both of those for our interferometer to work and give us 100% transmission one way or 100% reflection the other way.
Yeah.
And so we know that this is true. It's kind of like superposition is a system having kind of two states, not two states at once, but like having some character of having two states at once.
Yeah, the way that I've kind of been thinking about it recently and then how to explain this is you've got these two possible options, but as in it's either transmitted or reflected, but they retain some kind of potential to interact with each other, which is the interference that you were talking about before. Whereas if you have just a random classical splitting of lights, then it's not going to be able to interact in the same way. And it's really, you only really see that a single photon has been reflected or transmitted when you bring those two options back together again and you look to see how they interact with each other.
Yes, that's a good way of thinking about it, I think. Yes. Yeah.
And of course, everything you're saying about what happens at an interferometer, this is also true at classical levels of light as well, because like you're saying before, we can think about light as a wave.
Yes.
And so you would expect that at that last beam splitter, all of the light was either transmitted or reflected. I forget which one you chose as an example. But it's when you're at the single photon level that this weird quantumness kicks in, because as you said, it's like it's almost as if it's taken both of these paths at the same time as these two different options which are occurring simultaneously. And
we can never detect a split photon.
Yeah.
So we never actually, if we do the experiment where we look in the middle, we always find it in one place or the other.
Yeah.
But the result at the second beam splitter output suggests that somehow something's been both ways. Which we can never show because there's only one photon and it's not dividable.
Yes. So the next definition that I wanted to touch on, which might be kind of predictable, what's entanglement?
So entanglement is a kind of special property of that quantum systems can have. Really, it requires more than one quantum system, and I'm using system loosely. You could think of, for example, a pair of photons, which have a common past. Let's say they were created at the same time. So typically you might think of something that we've recently been talking about, which is photons produced by a nonlinear optical crystal, where you would essentially, you'd pump that crystal with a laser, an intense laser, and what happens sometimes is that single laser photons get absorbed by the crystal, and very, very quickly, 2 photons are created from that absorption energy.
Yep.
And the energies of those two created photons have to sum to the energy of the individual one that you put in.
Yeah, because you've got the general conservation of energy law, which is always going to be true throughout physics.
I mean, energy is not just deposited in the crystal, or at least hopefully not too much.
So you start with 1 photon from your laser, and you essentially split it in 2 inside this crystal because it gets absorbed and then re-emitted as 2 photons. And you know that the energies have to
add up. But also we know that this happens at a very, very specific time as well. It happens to an individual photon, one at a time, and so we know that at this time, this photon produced these 2 other photons, and the energies essentially are correlated. That's a word that is important, because the correlation means, in this case, that they essentially have to add to half the energy. The sum of the 2 energies of the 2 photons have to add to the original energy of the first photon. So that's all it really means. But it doesn't tell us what the energy of any of the output photons are.
Yes.
They don't have to be particularly fixed. There can be a broad spectrum, and indeed, so one can have a higher energy and one can have a lower energy, or they can both be exactly the same.
Yeah.
It's not fixed, and it's not fixed in advance necessarily. And so we say that, in some sense, the energy, once I know the energy of one, I definitely know the energy of the other, but before I've measured it, I can't tell which it is.
Yeah.
And that's really the type of correlation, the fact that the energies of the 2 photons are correlated, and they're very strongly correlated in this way. And there are more mathematical ways of saying this. That's a kind of a signature of entanglement, or one of them. Now, there are other things that we can be entangled in, not just energy. Light has a polarization, a direction in which the electric field wiggles, and there are similar correlations that you can get in polarization. If one photon is vertically polarized, if its electric field is in the vertical direction, the other one might have to be in the horizontal direction.
Yeah.
And again, in whatever case you decide to choose, once you've measured one in vertical, the other one's definitely horizontal. But even more interestingly, the actual polarization isn't fixed. I can rotate what I decide to be called vertical.
Yeah.
And what I decide to call horizontal. And so whatever angle I choose to decide to call vertical, these correlations are still exactly the same.
Yeah.
And that's the really spooky thing.
Yeah, that's what I was about to say. That's kind of like the crux of what makes entanglement really interesting. It's not just that you've got, let's say, 2 correlated particles, is that it's kind of independent of how you measure them as well. So you could do a different measurement which isn't, let's say, directly aligned to this correlation that you're interested in. And if it was just classically correlated particles, you wouldn't see anything interesting.
Yeah.
But if they're entangled particles, independent of how you measure them, you are still going to see this correlation. And like you said, that's the spooky bit.
Yeah.
That Einstein was saying in this famous spooky action at a distance.
It really is it shows that the correlations are not determined precisely until you make the measurement.
Yeah.
It's which correlation you're actually looking at isn't determined till you make a measurement on one of the particles. And then you know essentially in exactly which way these photons will be correlated. And that's the odd thing.
Yeah.
Because correlation is easy, right? The color of my socks is correlated. I could if my right leg has a blue sock on, the chances are that my left leg will have a blue sock on. That's easy. But for the color of my sock to not be determined until I've had a look at it, and then that determining the other color of the sock, that's a different thing entirely.
It's really hard to kind of create examples that make sense to people, because I mean, the example you just gave of your socks, there isn't really a good equivalent example that you can say for the entangled socks, if you want, like the quantum description. It's hard to describe what it actually means for the color of your socks not to be determined until you have a look at them.
And that's the kind of mysterious bit in the background that we can't actually make that. That's the thing that we kind of scratch our heads over, I guess.
Yeah. Because it's not quite the same as, I know I've got some socks on, but I don't really know what color they are, because you could know that in the classical world.
Yeah.
But in the quantum world, that statement is somehow a little bit different, and that's where all of this, these extra benefits that come from superposition and entanglements and all these different quantum effects really come from.
Yeah, and in some sense, the quantum correlations that you get from entanglement, they're stronger than those in classical physics.
Yeah.
We can do experiments that show this, that if you only had a classically correlated state, there would be only certain levels of statistics would be allowed.
Yeah.
In quantum, we can beat that.
Yeah.
We can do things that are statistical magic. I mean, really, if the world was classical, you'd have to be a magician to do it. You know, a real magician, not a conjurer.
Yeah.
You'd be a wizard.
That kind of brings us on to like how you actually measure entanglements, because the way I think of it is, you can, let's say you've got some systems, let's say a pair of photons that you think are entangled.
Mm-hmm.
The way that you test this is you can build a model, and you could say, well, I might see a certain amount of correlation. And let's say that there's even some parameter that I have no idea what it is, but it's some classical parameter which could connect one particle to the other somehow.
Yep.
You can show that you can see even stronger correlations than that through quantum entanglement. That's what we might refer to as a hidden variable model.
Yes.
And that's really what we're trying to beat. That's what you're saying. You show statistically that even if there was some classical thing that I don't know about and understand, the quantum correlations are still stronger.
Yes, they are. And it's something that people have been, I guess they've been testing this in many ways since the 1970s. And the first really good tests were done by Aspe in the 80s of these kind of correlations, and realistically showed that without some very, very kooky things going on, quantum physics was right, and the world is not necessarily as sensibly ordered as we might think. Essentially, these tests test something called local realism, which is locality basically says, if I want to measure the properties of the table right in front of us, I'd look at the table.
Yeah.
I'd measure it. Reality says the table actually has some properties that I can measure. So I need these tests, these statistical tests both locality and realism together in one lump. And the fact that we violate them says that local realism just is not a feature of our world at the quantum level. So either you've got to chuck out reality.
Seems like a big deal.
Or locality. That's also a big deal, right?
Yeah.
It's not something we see on everyday scales. But that's what the experiments tell us. And there were various loopholes in the early experiments. People thought, well, maybe there's not fair sampling of, because you throw away a lot of photons in these experiments. Maybe things are there's a problem there. Okay, but now we've got better detectors, and we can throw those statistics out. Maybe there was some kind of conspiracy that the detectors are talking to one another magically.
Yeah.
We can rule that out by putting them outside each other's light cones, so that they can never talk to one another. And there have even been proposals that you basically run your detection systems looking up in this, basically having them running determined by the cosmic microwave background in different directions that could never have been in contact since the beginning of the universe.
Yeah.
And so this would, nobody seriously believes that quantum physics is wrong now, but people were so spooked by this strangeness that they were looking for loopholes, and it's just not, they just haven't been found. So
we just had to rule out every possible alternative.
Absolutely.
I used to go into a bit more details, because you mentioned you could take these two detectors and place them outside each other's light cones.
Yes.
To go over what you mean by this. That's saying that even if there was some way that these two were interacting, you place them so far apart that if there was a communication that was going even at the speed of light, it wouldn't be able to reach the other detector in time to make any difference.
Yes, that's exactly it. They're just far enough apart that they could not possibly have communicated at the speed of light.
Yeah.
And we don't believe that there is any communication possible faster than the speed of light. So that would rule out an awful lot of the kind of strangenesses that people have proposed as ways around quantum correlations being odd.
Yeah, and you put all this stuff together, and it rightly so just sounds crazy, because it's so far detached from how we understand the world as it is in our everyday lives. You really have to kind of change your thinking a little bit when you start exploring quantum mechanics and all of these effects.
Yes. I mean, I have to say, when I'm thinking about quantum physics, I'm not usually thinking about this world.
Yeah.
I'm thinking about another world, a mathematical world that quantum physics goes on in. And it's a very strange thing, because that other mathematical world that we can't feel or see or touch or anything seems to control what goes on in ours.
Yeah, which again sounds absolutely extraordinary. How could that possibly be true?
How could it possibly be true? But when we do experiments, this world behaves as if it is, and it never ceases to amaze me, really, that appears to be the case.
I think a thing to point out, which when people are talking to people outside of, let's say, the quantum science space, so speaking, for example, to people in the general public, or videos that you see on YouTube and things, I think there tends to be this misunderstanding of what we say when we so take the example you had of a photon going inside an interferometer.
Yes.
We do a measurement to observe which ports that photon is in. What we mean by measurement means that photon interacts with something within the physical world. I think sometimes this gets kind of confused with, because people use the word observer. It's got nothing to do with, does someone with a consciousness actually look at that photon? It's actually interacting with the world that is that observation, in quotation marks, unless you disagree with that.
No, I think that's, I mean, this is touching on another problem that we have in quantum physics, which is the measurement problem, which is actually an unsolved problem at the moment still. The photon, for example, in your example, interacts with some kind of detector.
Yeah. And this detector is classical in the sense that, in the phrase that we would use, it decoheres the quantum state in some way. In other words, it's interacting with classical.
there's all sorts of processes going on. The photon gets absorbed by some system in the detector, and then there's an amplification process. Some energy is dumped in so that it can turn that individual quantum object into a signal that we can see on a screen or a click or a count or something like that. And something must be happening then, because somehow a quantum state that was ephemeral and intrinsically probabilistic.
Yeah.
Because we didn't know the photon was there before we detected it, suddenly became a big certain classical blob that we can just count.
Yeah.
And that's another area that we're not absolutely certain what's going on in, but certainly the interaction with the classical world to change our kind of superposition state into something real.
Yeah.
Is very odd. That's essentially where the interaction comes between this kind of extra strange world and our world. Because this strange world has a very easy, simple set of rules governing it.
Yeah.
The real complication comes when we try and mix the two.
It's almost like, kind of like you're saying there, it's almost like we have some very fixed, determined ways in which the what we considered like our world interacts. We know the laws pretty well for how the classical world interacts with objects. Mm-hmm. So when we introduce a quantum particle or something into that world, it suddenly has to obey by our laws, and that kind of changes how we have to see it as well.
Yeah. Although I have to say, if I were to give a personal point of view, I'm very much of a believer in the fact that everything is quantum, even the classical things that we have, and that somehow we're not quite describing the classical things properly.
Which I think is definitely true, in the sense that every mathematical equation that we can use to write down how the physical world is interacting. So you mentioned Newton. So let's take Newton's laws of gravity. They have to. They're only ever going to be an approximation to what the real physical world is doing. Yes. And it's an approximation in the right kind of circumstances. So it's never going to capture the full picture, because writing down the full picture in an equation would be ridiculously complicated and just impossible really to manage.
Yeah.
So we have to kind of make these shortcuts. So it's true that the kind of by extension we have to be in a quantum world as a whole. It's just we see the quantum world with certain restrictions in place, and that's what we call the classical.
I would agree. I think all you can hope from physical theory is that it gives you accurate predictions in some regime.
Yeah.
And that I'm happy with. The best physical theories give you an insight outside that.
Yeah.
Just around the edges, allow you to maybe predict a bit more. That was Newton's law of gravity, his advantage over Copernican. Ptolemaic.
He could actually start to predict how things outside the solar, even just like beyond the Earth and Mars actually interact.
The dropping of an apple suddenly tells you about planetary motion.
Yes. Yeah. Exactly.
You know?
Yeah.
It's a really quite profound thing, right? The problem. So with quantum physics, we have a good mathematical theory that exists in this other world. Mm-hmm. The problem we have is with pushing the interpretations onto our world. That's
that's definitely a good way of seeing it. So just to wrap up, same question that I've been asking everybody so far, because I'm getting some really interesting answers to it, which has been great. What's your favorite random science fact?
Really? I think it's the unreasonable effectiveness of mathematics in describing the physical world. Why can I solve equations to predict what's going to happen, or to tell me what happened in the past? If I make a measurement of a system now, there's Laplace who said, if I know the positions and velocities of all the particles, then the past and the future is just a matter of doing the sums.
Yeah.
Why is that true?
That's an excellent question.
That's my favorite. I mean, it's clearly factual because we can do it. We use it every day.
And surprisingly, that kind of extends into the quantum realm as well, right? So if I know where a particle is now and what direction it's going in, even let's say it was a photon and I initially didn't, I might not have known when it was generated where it was going. That particle is still going to interact as though it's always been traveling that direction that it was before. So in other words, if I know where a photon is now and where it's going, I still know where it was before, even if it's a quantum particle.
Yes, within the restrictions imposed by the uncertainty principle, you know exactly that. Yes, and that's this kind of mathematical rules applying quantum physics as in every other area, and that is a source of amazement to a lot of people, not just me. We don't always think of the future as predictable, but at the microscopic level, it definitely is. And when the reason why we don't think so if I toss a coin, why can't I predict the answer? The reason why I can't predict the answer, heads or tails, is because it's a complicated business. Yeah, the equations are hard to solve. Not only are the equations hard to solve, the exact force that I've tossed the coin with, we haven't got a good measurement of that, and the exact height at which I catch it, that doesn't, that if that changes very slightly, then it changes heads to tails. This is a very sensitive system, and our world is very, very sensitive to initial conditions. Yeah, in other words, it's not that you can't know what the outcome is. It's just that it's a really difficult problem to solve because it requires you knowing things to really, really high precision. Yeah, and the computational power required is enormous. Yeah. So that's why it's tremendously difficult. But fundamentally, maths will do it if you've got long enough, and you've got enough calculations to be able to. You can do enough calculations quickly enough. Yeah. So it seems like I'm backtracking a little bit here now, but the example you gave of a coin flipping is a really good one because, as far as we know, the only way to really get something which is unpredictable and something which is truly random, in other words, we can't model its behavior with a system of equations. It is just random chance. Comes from quantum. Yeah, if we believe in quantum physics, and we have no reason not to, all of our experiments tell us it's true, then a superposition of heads and tails gives us a random coin, a truly random coin that we could not predict the answer to. Let's bring it back to the example that we started with. So a photon at a beam splitter, is it transmitted or is it reflected? That's the same as our heads and tails, but that is different from the coin. That is truly inherently random which way it's going to go. Absolutely is. And there are random numbers routinely generated in exactly that fashion that you can find on the internet. They publish these random numbers that are generated by photons, essentially hitting a 50-50 beam splitter, going left or right. And we use this now. Yeah. If you want a really truly random number, you can look those up. Yep. And you can, if you really wanted to, you could go away and you could try and find some mathematical model or description that kind of finds a pattern, but you're never going to. That's kind of what we're saying, right? There's no pattern. That pattern just does not exist. There's no correlations between one photon and the next. There's no correlation between one photon and the 100,000th later. There's nothing there. It's just truly random, which, although it appears random, my standard coin flip is not truly random. Yeah. I think that's an excellent point to leave it on. John, thank you very much for your time. It's been a really interesting discussion. Yes, that's been great, Ashley. I really enjoyed that. You've reached the end of the podcast, which probably means that you enjoyed what you're listening to. So please don't forget to like, follow, subscribe, and share this podcast series as much as you can. The more you do those things, the better this podcast is going to be. Don't forget, you can always contact me by email at ash@crackingquantum.co.uk. And please join me again for another episode of Cracking Quantum.